When we hang a weight on a spring, the spring stretches. When we add additional weights, the spring stretches still more. When we remove the weights, the spring returns to its original length, right? We say that the spring is elastic. When a batter hits a baseball, he temporarily changes the ball's shape. When an archer shoots an arrow, she first bends the bow, which springs back to its original form when arrow is released. The spring, the baseball, and the bow are examples of elastic objects. Elasticity is the property of a body which it experiences a change in shape when a deforming force acts on it, and by which it returns to its original shape. Not all materials return to their original shape when a deforming force is applied and then removed. Materials do not resume their original shape after being distorted are said to be inelastic. Clay, dough, and lead are all inelastic materials because they are easy to distort permanently. Let us go back to the spring example. By hanging a weight on a spring, we are applying a force to the spring, right? It is found that the stretch is directly proportional to the applied force. This relationship is noted by the British physicist Robert Hooke in the mid-17th century. It is called Hooke's law, and it states that the amount of stretch or compression is directly proportional to the applied force. Let us apply this law in a question. A certain tree branch is found to obey Hooke's law. When a 20-kilogram load is hung from the end of it, the branch sags a distance of 10 centimeters. If instead a 40-kilogram load is hung from the same place, by how much will the branch sag? How about if a 60-kilogram load were hung from the same place? A simple look in this problem may prompt us to answer 20 centimeters, since we double the force exerted by the object by doubling its mass. Therefore, the amount of compression should be doubled. But let us analyze the problem to see if we got that correctly. You see, there is a 20-kilogram load here which is hung from a branch of tree. This mass makes the branch sags for a distance of 10 centimeters. Remember that Hooke's law explains the direct relationship of the amount of a stretch and the force applied into it. We can easily compute this by ratio and proportion. Our first ratio would be 20-kilogram load, which by the way is in mass, so we need to find the force this applies by multiplying with 9.8 meter per second square, and that gives us 196 newtons over the amount of compression, which is 10 centimeter. On the other side of the equation is the 40-kilogram load, which we converted to force by multiplying with 9.8 meter per second square, and so we got 392 newtons over x, which is our unknown. We cross-multiply these values to get 196 newtons multiplied by unknown in this side, and for this side we have 392 newton multiplied by 10 centimeter. This will give us 196 newton x in this side equals to 3,920 newton centimeter at the right. Because we are looking for x, which is the amount of compression with the unit centimeter, we divide both sides by 196 newton, and that gives us 20 centimeter. The second question, how about if a 60-kilogram load was hung from the same place? Using the same method, since the mass exerted thrice as much force, then according to Hooke's law, we will have thrice as much compression. So 10 centimeter multiplied by 3 is 30 centimeter. Okay, it's very easy, right? I hope you understand the simple explanation of how to compute the elasticity of materials and the concepts you need to remember when we deal about elasticity. That is all for this video. If you have questions or insights, feel free to include them in our discussion board. I am Gilmar De Castro and see you in the next video.